All right, guys, ready? I'm gonna show another applied type of part of math. I think, and I got another video to show you. But first thing I want to do is I want to show you the equation that we're going to go with for this. So I think some of you have seen this in science. Distance equals speed divided by time. 1/2 AT squared. You ever seen that? So this is the equation for a free falling object. Okay, any free falling object will deal with this. So D is distance, and we can have it in feet, or we can have it in meters, or we can have it in miles, or whatever. Okay, but for right now, we're going to use distance in feet. So which letter of the quadratic, X or Y, do you think D represents? Y. Okay? Is everyone okay with that? Yeah. Now, the 1/2 is just a constant. It comes along for the ride. The A is not necessarily the same as the A value you deal with standard form is ax squared plus bx plus c. But the A is the acceleration of gravity. And being we are falling back towards the Earth, it's negative. Is it okay? Now, you could have the acceleration of gravity, if we were dealing with meters, as negative 9.8 meters per second squared. Yes? Does anyone know what that converts to as far as feet? Do me a favor. If you have your phone and it's still on, and you can get on to the...
Wait, are you, like... the 9.81 meters per second.
That is true, but I want it in feet.
Oh.
Somebody tell me what the acceleration of gravity is as far as feet per second squared.
$32
Thank you. So negative 32 feet per second squared. Okay? Now, time here is going to be in second, but what do you see with that? So this will be second squared. So I want you to realize something with this problem. Let me split our screen. This will make more sense. Dual page. Okay. So we have, let's make this work. Distance is y. A is this. T squared is actually our x value. Is that okay to say? We okay so far? So I want you to kind of think. If I have distance is 1/2 the acceleration due to gravity, negative 32 feet per second squared. Notice the second squared is on the bottom. You still with me on this? Times t. Times t. Okay? Times t, which is in what squared? So t is in second squared. Okay? Which I technically could put that over 1. What looks like it will cancel out because it's on top and on bottom of a fraction? Seconds what? Squared. So if second squares cancel out here and here, what label does it appear our answer will have to be in? Feet. Is feet a distance? Does this make sense? So we're going to come back to this equation. We're going to talk about it, and we're going to play around with it a little bit. But some things we have to realize. That the units, if they're on top, they're on top. If the units are on bottom, they're in a denominator. They do it that way for a reason, so you can use something called dimensional analysis, which allows you to cancel out, reduce like a fraction. So if you had like 2/8, that would reduce to 1/4. But the same thing is, if you have a unit on top and a unit on bottom, they cancel. Now, let me ask you this. This is not going up here on the screen, but let's say I had feet squared on top over feet on bottom. That's the same thing as the tug of war. So if I had feet squared on top and feet on bottom, who wins? Top and bottom? Top. And then you have just feet. Does that make sense? Now, dimensional analysis is something that will get you through science really well. Okay? Because you start understanding that things are in certain terminology. Meters per second. That's meters on top over second. Okay, acceleration, meters per second squared, or feet per second squared. Feet are on top, meters are on top, second squared is on bottom. So that's where this kind of math applies. So I want to pull up this, bless you, I want to pull up this video for you. And I just want you to watch it. I'm going to put some information over on this board from what the video shows. There's no talking about it, but it's basically the highest. I'll leave it like that. 58.8. Had a butt shield for a reason. Did the world's worst enema if you did it. Okay. So you get the gist of where we're at? Yeah. So things that I know. So I know that this equation is going to stay here. So I'm going to go back to a full screen. No, that's not what I wanted. I want to go back to single plate. Oh. Are you sure?
You have to accept this kind of behavior.
I want to run away? Okay. That's our message for the day. All right, so things that this video told us. Let's go back here. 58.8 meters. If you have your phones, please.
Yes.
Will you see about converting 58.8 meters into feet, please?
What is it?
58.8 meters converted into feet. So you should have some sort of thing on here.
192 feet.
192 feet?
Yeah.
Sweet. How much?
0.9.
192.9?
Yeah.
Like it. Does everyone feel comfortable with that? Seem appropriate? I mean, a meter is a little bit longer than a yard. A yard is 3 feet. So if I were to triple, let's round to 60, I get 180. And if being a meter is longer, that would make sense. Would that seem to be an appropriate answer? Okay. Things that they also tell us. He was doing 123 kilometers per hour when he hit the water. I don't like kilometers per hour because it doesn't register to me. So will you find it into miles per hour on your phones. 123 kilometers per hour is how many miles per hour?
76.4 miles.
Holy cow. I don't know about y'all. I don't know about y'all. You know, if you're in your car doing 76.4 miles per hour, you know, whoop-de-doo, right? We're talking about we are accelerating towards the earth and going to land in water, and we're hitting that water at 76.4 miles per hour. Woo! Woo! Wow! And then they tell us that it is 3.58 seconds. And we understand. I mean, we can convert this to hours, but we don't need to. Okay. So, values that aren't all that important to us right now is the 129 feet, definitely, or 192.9 feet. So let's put this into perspective. 192.9 feet. This ceiling is about 9 feet tall. Okay? So if I do 10 of these ceilings, that puts me at 90 feet. So we're at like 20 of these rooms. Maybe a little bit more. So a 20-story building. There isn't a building over in the tech center that is that tall. Think about that. You're driving over to the tech center, you know, right over here. Those are some pretty tall buildings. I don't know how many of you will be going, dude, I jump off that 12-story building. This guy went further. Okay, in the water, which is great. And he survived. Now he kind of gets up and he's like, well, all right, dude, where am I? Mommy, is that you?
I jump off of that if I had shields and protection like you and all that stuff.
I agree. So here's what I would like to do. With the information they have given us, with the 192.9 feet and the 3.58 seconds that it took there, I want to use the original equation I have, and I want to verify the acceleration of gravity in feet per second squared. Now I already said, we already found it to be negative 32 feet per second squared, yes? Wasn't that what we found earlier? What does 9.8 meters per second squared convert to? Okay? So we have this information that we know, which is great. Okay? Let's go back to our dual page. Okay? So we're going to plug into this equation, and I want to verify this number here. Okay? That is the acceleration of gravity. The 1/2 is still there. Does that make sense? The 1/2 is a constant. So I know that distance. Distance, what do we know? What's our distance? Help me out. How much? Okay, so distance is 192.9 feet. We found that because the video told us that it was in a certain amount of meters. We converted it look it up online and found it on our phones. Do you agree? Are you following me still in this transition of things? So this is, and the neat thing is, this is a squared scenario. Okay? So it's a quadratic. It's a parabola. It's a parabola that opens downward because I have this negative here, right?
Yes.
Okay? So this will be a parabola that looks like this as far as the acceleration, and it has to do with this guy hitting water. Okay? So distance equals 1/2 AT squared. So distance equals 1/2 AT squared. Okay? I'm going to try and verify the acceleration of gravity. Okay? So they told us 192.9 feet, or we converted it, because they gave it to us in meters. And then they told us it took 3.58 seconds from the time he left that platform to the time that he hit the water. 3.58 seconds, 3.5 seconds. Think about this. Let's do 3 seconds. This is what it feels like. Ready, set, jump. Hit. Okay? People are like, dude, it's 3 seconds, no big deal. Okay? If you're accelerating towards the water, you're probably thinking of a few things. During the jump, going, one, you're probably saying, feet first, keep the legs closed. Okay? That's a hard jump. That's a long time for you to think. That's a long time for you to go, whoop. Right? And probably during that, you're not going to hear a whole lot of stuff. Your adrenaline is probably going about 1 billion. And you're like, yeah, and so you're like in this euphoric world where you hear just the rush of the air. And it might even seem kind of like time is standing still a little bit because it's wow. Okay. So time d equals 1/2 at squared. So I know that our time, I'm going to plug in 3.58 seconds. Does that make sense? So now I know d, and now I know t. But what do we know about t? What do we know about t? It's squared. So let's make our units work. Okay? So I'm going to plug into this equation right here. And we're going to verify a. Okay? We know it's a quadratic because it's what? Squared. It's not a straight line, it's a quadratic. It's a parabola. In this case, it opens downward. We know it opens down because we have a negative value up front. Okay? So let's plug in. D, 192.9 equals 1/2 is a constant. A, we're looking for t squared. Okay? Let me put my units in as well. I need to put feet in here. Okay? Feet there. Is that okay? Can you see feet? Okay. And then we know that we have 3.58 seconds squared. Notice how I have the squared outside. It's not 3.5 and then seconds squared. It's 3.5 or 3.58 quantity seconds squared. Okay. Can we do a little bit of the math? Okay, I need your help. So I know, because we discovered this, that this goes here and it goes here. So 3.58 is squared as well as seconds squared. So I know that I have 192.9 feet, still with me? Yeah. Equals 1/2 a second squared now. Can someone tell me what 3.58 squared is? It's not quite 16. It's bigger than 9, though. 12.81? Okay. Do we agree?
Yes.
Yeah.
Okay. So now I would like to start getting a by itself. Okay? Would it make sense to multiply this by 2 and this by 2? And if I did that, what would happen with our 1/2? Yeah, this reduces with this. That gives me 1a, and 1a is the same thing as a. Okay? What is 2 times 192.9, please? 2 times 192.9. It's not quite 400. Agree? 385.8? I know. That's why I asked, just to make sure. 385 point. No, notice feet still stays as feet. Nothing's gotten squared. The reason this became second squared is because this outside the quantity went to both values. Okay? So now I have equals 12.81 seconds squared times, what value is still there? A. So if I want to move this over here, what do you think I should do? If I want to move this over, this is being multiplied times A. So what would undo multiplication? Division. So I have 385.8 385.8 feet over 12.81 seconds squared equals A. Will feet or seconds squared reduce each other? Good. They're two different units. Good. But will 385.8 and 12.81 reduce? Yeah, it's going to be a decimal, yes?
Yeah.
So will you do on your calculator? Go 385.8 divided by 12.81. How much? 30.1 feet per second squared. Okay? What did we say A was originally? No?
Or 1A.
Negative 32 feet per second. We got 30.1 feet per second squared. So did we make an error? Did physics not work? What do you think? So, do you agree that 30.1 and 32 are pretty close to each other?
Yes.
Now, what might have happened a smidge from the platform to goof this up just a smidge? So I want you to think about this. He was at this platform, and then down below, we had water, yes? And we knew that this was, oh shoot, it was 58.8 meters, and we said that that was, how many feet? How many, shoot, 192, what was it?
It was like 192.59.
192.9, okay? 192.9. 192.9 feet, okay. Okay? Still with me? And they said from here to here took him a certain amount of seconds. 3.58. Okay? So they knew this distance here was 192.9 feet. Still with me? And he went this way. When he jumped, did he just go like this? Step off? Oh, he jumped up a little bit. There you go. So he probably increased the distance. So he kind of jumped up and out a little bit. So he jumped up a little bit. So we are off a smidge on our math because the video only accounted for the height of the platform to the water, not him jumping up and then in. Make sense? So our little bit of error is caused because the video did not account for him jumping up and then heading down. The platform was only 58.8 meters or 192.9 feet. But truly, he actually went a little bit further because he jumped up a smidge. Does that make sense?
Yeah.
Wow. So, we didn't discover mathematically that the acceleration of gravity somehow changed with this video. We had to realize there had to be a small amount of error because of something. If we went back and watched that video one more time, we would have seen that he did indeed jump up. And we all agreed that he did jump up. Now, how far did he jump up? That's information that we don't have available to us at this point in time. But that's why there's a slight error in the acceleration of gravity. Are there other places where errors might have taken place? We might have rounded. We might have rounded here or there. Yes? You know, when we were doing our math, is 58.8 meters exactly 192.9, or was it a continuing decimal? So I'd say there's probably a start part of a continuing decimal here. Okay? 3.58 seconds, I think that was a given constant. We knew that. So I think that, and then we probably also made an error here. When we squared this, is 3.5 out, 3.58, is that exactly 12.81, or was there more of a decimal? I would say there's more of a decimal here. So we had little places that small little errors could be accounted for. Does that make sense how I said that?
Yes.
So again, we did not discover that the acceleration of gravity jumping off of a plank way high up into a river below, or a pond below that's probably pretty deep. We didn't discover some anomaly in the gravitational pull of the Earth. Okay, but there were certain places where small little errors could have taken place. And I like that our 30.1 feet per second squared is pretty darn close to negative 32 feet per second. Per second squared. Now, again, we say this is negative. Why is this not negative here? We're accounting for an acceleration. The reason we put a negative value into it is we're falling towards an object. That's why it's negative. So in science later, you need to start realizing why are some of these numbers coming about, and it wasn't just some arbitrary value that came out. Okay? Many years ago, they would have gone like this. Let's drop this. Whoop, boom. How long did it take? And they had some unit of time. And then somebody else went someplace else saying, hey, let's go to this real tall place. And whoop, how long? Oh, and they started realizing that it's a constant amount of gravitational pull. Okay? So were people in the olden days dumb? No, they're pretty innovative. Because now, because of their discoveries that are still true for today, allow us to continue to use the math as a tool that goes with science. Okay? Like yesterday when we talked about the braking distance, we were talking about a parabola. Okay? Which is pretty cool. Today we're talking about acceleration of gravity, jumping off of a cliff or off of a platform next to a cliff that went to water. Okay? These are both applied versions of it. Now, here's pretty neat stuff. We can play around with that equation, and we can find a whole lot of different things. Okay? If we were to truly just continue to use this equation, things that we know. This has got to be a constant because we're jumping on the planet. If you went to the moon, it'd be different. You went to Venus, it'd be different. You went to Mars, it might be different. Okay? If you went to Jupiter, it'd be different. Why? Because gravity's different on different planets. Okay? And I understand you couldn't jump on Venus because you have sulfuric acid, or some sort of acid, I think it's sulfuric, in the majority of the planet. It makes it hard to survive. Okay? But, being we know that this is a constant, we can start figuring out what happens at time, and we can sit there and say, well, if we were to jump out of an airplane, and let's say we knew that it was 30 seconds before we would hit the ground because of our height, you might be able to say, let's have a little bit of fun on the free fall before we open our parachute. Okay? Now, jumping out of an airplane sounds pretty cool to me. Okay? Now, jumping out of an airplane where you're clicked into a static line right away, okay, yeah, that's going to be pretty cool. Okay? And then I realize that sometimes you'll be harnessed into some guy behind you who you're kind of like this, in this harness, like, hey, and this guy's holding you up and going, okay, ready, we're going to jump. You're like, no, mommy, and he jumps. It has a bigger parachute because the mass of the two of you would require a larger parachute in order to slow you down enough that you didn't shatter your femur as you hit the ground, which I heard is a good idea. Because the femur sounds like a 2x4 snap. It's the hardest bone in the body to break. It's a medical emergency. I don't recommend it. I don't recommend it at all.
It's just a flesh wound.
Yeah. You don't put a Band-Aid on it. As my mom would say when I used to get hurt as a kid, go lay on the couch. There was one time I broke my thumb when I was a kid. I was riding my bike real fast, and my foot slipped off my pedals, and I grabbed the fork, my front forks that hold the wheel, with my right hand, and my thumb went in to the spokes, and I'm sitting there in the road, and I'm 9 years old at the time, and I'm looking at my hand, and my thumb is going this way. And I still remember to this day, a woman in a yellow Cadillac, four-door Cadillac, brown hair. Okay, this is how I remember this woman. She pulls up alongside me. I'm sitting there looking at my hand, kind of sitting in the street of my neighborhood. She's like, "Are you okay?" And I hold my hand up, and I said, "I broke my thumb." I mean, it's obvious. It's going the wrong way. And she goes, "Oh, okay." And she drove away. And I honestly thought she was like going to turn around and come back and, maybe like take me home. I was a few streets away from my house. I watched her drive away. Mom, I'm 9 years old. My thumb's going the wrong way. I'm sitting in the road. Obviously, I crashed my bike. My bike is here. I'm here. My thumb's going the wrong way. Are you okay? Yellow Cadillac, four-door, brown-haired lady.
She's probably
And
dead.
she left. So, what do? I guess that's not going to help. Guess I can't use the wimpy card of my thumb's going the wrong way. So I got onto my bike. I'm still looking at my thumb. And I put my right arm onto my steering wheel. And I start pedaling. And I'm trying to think, okay, my thumb's going the wrong way. Okay. I get home. I walk in the house. I still remember my mom is talking to the next door neighbor. They're in the living room. And you know how moms are. They're gathered back and forth. Like there could be an atomic explosion, and they'd be like, "Don't interrupt us." So I walk in, Mom. What? I broke my thumb. It's going the wrong way. Oh, just go lay on the couch. This compassion. Well, apparently this couch had healing properties. So I lay on the couch, and I don't know how much time took place because I'm 9, and so it could have been a year took place, or it could have been about 3 or 4 seconds. I don't know, somewhere in between those. Probably closer to 3 seconds than a year. So then my mom comes. She goes, "Let me take a look," and she's looking at it. She goes, "Oh yeah. Well, let's wait till your dad gets home and see what he says." Okay, my thumb is going the wrong way, and it's swelling, and it hurts. So I wait for my father to get home. Dad looks at it. "Oh, yeah, you broke it." So because my dad, who owned a drapery manufacturing plant and made many blinds and verticals, his expertise, because he was on the volunteer rescue squad when we lived in New Jersey, was able to decipher that my thumb was indeed broken.
Whoa.
So they take me over to the emergency room. Doctor comes in. "Yeah, it looks broken, but we have to x-ray it just to make sure." It's going the wrong way.
We did that
Literally
with my foot.
facing backwards.
We did that with my foot last year.
It's going the wrong way. So, needless to say,
Nurse was just like, "Oh, just go lay down."
yeah, go lay down. It's healing properties.
She made me lay down for 3 hours until I had to go home.
Healing properties, I'm telling you. So, needless to say, they were able to straighten out my thumb and put it into a cast. And I'll tell you what, when you're sitting there going, "Okay, this is what we're going to do, and it's going to hurt," and this is how medical practices worked back in the day. Now they'd actually probably, let you take a little ibuprofen. Actually, what they'd do is probably give you a mild narcotic, so you'd be like, "Ooh, I'm in La La Land." No, now it's like, "Dad, come on over, hold your son while we straighten his thumb." I'm 9. My dad is 300 plus pounds, 2 tours in Vietnam. Like he's kind of tough, a lot tougher than I ever was. So he's like, "Okay, son." So my arm's out there. He's got me pinned down. And then my thumb, I feel being pulled and tugged in certain directions that probably shouldn't have happened.
And you just hear popping.
There was no popping because it was the bone itself was broken right back here. So they straightened it out and they put a cast on it. I went home, and so then it became the cool thing at school going, "Hey, look at Stuart's got a cast."
Whereas instead of like having people say no, I actually had to ask one of my friends because my shoulder was completely dislocated, like out of the socket. I went, "Okay, can you pull really hard on my arm?" And it made this really gross popping sound, and he looked sick. And I'm like, "Why do you look sick?" I was in pain.
I understand. All right, I'm going back to our worksheet that I handed you yesterday. Let's talk a little bit about this. We got about 12 minutes left. We can go over this last example. And then the expectation is for tomorrow that the appropriate worksheet is done. So, if you have yesterday's notes, great. If you don't, sit back and listen. It says a building, or a person is building a rectangular enclosure for an oriental grass plant in their yard. She purchased enough bricks to make a perimeter of 20 feet. Use this information to answer the following questions without using a calculator. Oh. All right, I think we do this. Let me go back to the full-size screen. Let's see. Single-page display. So things that we know is she has enough bricks to have a perimeter of 20 feet. Okay, now, perimeter is a distance. Do you agree?
Yeah.
So if I were to walk around the perimeter of this room, I'd walk around all the edges. I could say how many feet or how many steps or how many yards or whatever it took to get all around. So that's why it's not squared or anything like that. Okay? So she's using these bricks. Things about perimeter, I know this equation, 2L plus 2W. If it's a square, perimeter is 4 times the side length. I mean, those are some things that are go-to. I don't know if we're going to make it round, but if we were going to make it round, we have C equals 2 pi r, where pi represents the diameter of a circle divided by, or the circumference of a circle divided by the diameter, and we find it's 3.14159, just take it out a few spots. So those are just some things that deal with perimeters that are go-tos right now. All right, now it tells us if the length of the rectangle is x feet long, okay? So if the length, and it says we're using rectangles, so this deals with rectangle, so I don't need this or this any longer. Okay, if the length of the rectangle, length is equal to x, then the width must be represented by 10 minus x. Okay, so the length is a certain ratio of x, and the width is 10 minus x. Draw a diagram of the rectangle and explain why the width must be 10 minus width. Okay, so rectangle, let's see if I can be creative. I have a length, I have a width. We were indoctrinated in elementary school to know that the length was always longer than the width. I will tell you right now, and you'll learn next year in geometry, that length and width are arbitrary. They can one can be longer than the other. It doesn't have to be modified, but let's go with what dear Miss Smith had told you when you were in elementary school because she was reading it out of a book. Length equals x, width equals 10 minus x. Okay? All right, so if the perimeter is 20 feet, so we have this way and this way. If it's a rectangle, we know the top and the bottom, but the length and length, or the width and width have to be the same. So if we know that the length is x, the width has got to be 10 less than that. Because between the width, God bless you, you know that you can't have a width that's longer than 10. Why is that? Because if the width is longer than 10, then that means that our perimeter thing falls out of the equation because we still have 2 lengths to worry about. Okay? And then it says, so the area function must be area equals length times width. Oh, okay. I remember working with area. Area of a rectangle is length times width. Okay? Area is length times width. Find the dimensions of the rectangle that maximize the area. Oh, okay. I think I can do this. Area is equal to length. We know that length is how much?
10, 20.
Length is how much? Length is how much? X, thank you. And width is how much? 10 minus x. So theoretically, I could distribute over, and I could get a equals 10x minus x squared, which also could be negative x squared plus 10. Plus 10x, which is a parabola. Do you agree? Does a parabola open up or down? Down. Why is it open down? Negative x squared. So it's this parabola. Okay? So a portion of this parabola is probably unusable space, but I will tell you that our vertex of our parabola, if we were to go this way, somehow like this, this is going to be area, and this is going to be length. So our vertex will tell us at what length, using our axis of symmetry, that the components at this length and this will give us our maximum area. Okay, I think I can do that. We know that negative x squared plus 10x, negative x squared plus 10x, negative x squared plus 10x. Things that we do know. I do know that I could factor this. I could get this to be x, negative x plus 10, and set it equal to 0. If I set it equal to 0, that gives us where it crosses this axis, so I know that x equals 0. Well, I certainly am not going to have a cut of 0. Okay? But what would our width be? What would this be? How would I set this? What's the answer here? I would subtract 10, so negative x equals negative 10, so x equals 10. And I probably won't have a maximum cut of 10 either, because that would be 10 by 10, which would be lying right on top of itself, which does indeed give you a perimeter, but we want to maximize the area. So somewhere between 0 and 10 will be our length. Okay? I can find the vertex because I know the negative b over 2a and plug in. Okay? So help me out. Negative b is what? Negative b is what? How much? Negative 10. Negative 10 over 2 times a. A is negative 1, which gives me 10, comma. Oh, I could plug this in and get an, let's see. Negative b over 2a. I'm sorry. So that should have been negative 2. So that should have been negative or positive 5. I'm sorry. If I could do math, I'd be a really good teacher. Okay, so at this distance at 5, if I made a cut of 5, this is going to give me my maximum area. So if that's 5, let's plug it back in. I can plug it here. 5, and then negative 5 plus 10. What is, that gives me 5 times 5, which gives me 25. Shh. So if I had my value of x, which is length of 5, I would then find that my maximum area is 25 of this particular rectangle. And if you figure this out, you would realize if the length is equal to 5, because negative x plus 10 is equal to the width, and we found that length being 5 is also x, we'd also find the width to be 5. So what did we just find out about this rectangle? It is a makes parabola. I have a length of 5 and I have a width of 5, so this rectangle is a square. Yay. Okay, now does it always work that way? No. Okay, what is a feasible, what is a feasible domain? A domain goes from here to here on this problem. So it has to be bigger than 0. And it has to be less than 10. That's our feasible. It can't be equal to 10, because if it was 10 and 10, it would fall on top of itself. And I'm not going to have a cut of 0. Our range goes from here to here. Okay? Our range will go from 25 down to 0. Okay? And we approach both. Okay? I guess we could say we could have a square bracket on this because it can have an area of 25, but I'm not going to have an area of 0. I can approach 0, but I won't have it. I mean, if I were to find this point right here, I'd have a really, really small length, really long width, and a really small area. But this allows me to maximize what my area would be. So, guys and girls, this is what your assignment was last night. Now I want you to finish it, please. And I will check it out. I've got to make sure I give the right page. Okay. It is worksheet number 9. Let me go here. Worksheet number 9. And it looks like it is only on page 117. There's nothing more. Okay? I think you can do it with what we did. If you already did it, then watch the TV tonight.
Nice. On me. On me.
If you need a picture of the page, I think it's supposed to take a picture, but if not, it's in the basket. If you need a picture, it's only one side. It looks like pretty quick and easy.